Welcome to the deep dive. You know, the batteries powering our lives are, well, truly marvels of modern science.
They really are.
And today, we're going to pull back the curtain on a critical yet often overlooked component, the electrolyte.
Absolutely vital.
We'll be using the book Electrolytes for Lithium Batteries as our guide, specifically diving deep into the first 4 chapters, which lay the groundwork by exploring the materials themselves.
Right.
Think of this as your express ticket to understanding what makes these batteries tick.
Exactly. And this isn't just about listing chemicals. It's, about understanding why certain materials are chosen, the challenges researchers face, and the constant innovation driving this field.
Yeah.
The authors of this book have compiled information from the cutting edge of research and even patents, so it gives us a real sense of both the fundamental science and its practical application.
Okay.
Our goal here is really to extract the most important insights from these, well, pretty dense chapters and make them accessible to you.
Okay, so let's kick things off with Chapter 1, Non-Aqueous Electrolytes, Advances in Lithium Salts. This chapter comes to us from Professor Wesley A. Henderson at Pacific Northwest National Laboratory.
Right.
Now, when we talk about a battery, we know there's a positive and a negative end, and something needs to carry the charge between them. That's where lithium salts come in, right?
Precisely. Lithium salts are the source of the lithium ions, those tiny charged particles that shuttle back and forth between the electrodes during charging and discharging. For this to happen efficiently, the salt needs to dissolve well in the battery's solvent and break apart easily into these ions.
Makes sense.
Professor Henderson's chapter examines a wide range of lithium salts, comparing them to the current industry workhorse, LiPF₆, lithium hexafluorophosphate.
Right, the main one.
And looking at their core properties in non-water-based or non-aqueous solvents. Because, lithium reacts violently with water, so that's a big no-no in these batteries.
Yeah, definitely can't have water in there. Here's a fact that really jumped out at me. Many of the negatively charged parts of these salts, the anions, were initially developed while scientists were trying to create superacids.
Yeah.
Acids even stronger than something like sulfuric acid. Why is that relevant?
That's a fascinating historical tidbit, isn't it?
Right.
A key characteristic of a superacid is its tendency to give up a proton, a positively charged hydrogen ion, very, very easily.
Okay.
The counterpart to this is that the resulting anion holds onto that proton very weakly. So in the context of battery salts, we generally want an anion that weakly interacts with the lithium ion.
Ah, I see.
This allows the lithium ion to be more mobile in the electrolyte, which, leads to better battery performance.
So it's like the anion needs to let the lithium ion go off and do its job carrying charge.
Exactly. But it's not just about how acidic the precursor was. How these salts behave in the actual solvent inside the battery is actually quite complex.
Right.
Factors like the size and shape of the anions, their steric bulk, as chemists say, and how much the positive and negative ions like to stick together in solution, that's called ion pairing,
Okay.
all play a significant role. So while gas phase acidity gives us an initial hint, the real performance test is inside the battery itself.
When scientists are evaluating these lithium salts, what are the crucial things they're looking for? What's top of the list?
Top of the list is stability, definitely. The salt needs to be a good citizen within the battery, basically, not reacting with the other components over many charge-discharge cycles and across a wide range of voltages.
Okay.
It also needs to be stable at higher temperatures, which is vital for safety and, well, how long the battery will actually last.
Right, longevity.
Interestingly, though, sometimes a little bit of controlled instability can actually be a good thing.
Controlled instability, that sounds weird. How does that work?
Well, think of it this way. The breakdown products of some salts can contribute to the formation of a crucial layer on the battery's electrodes called the solid electrolyte interphase, or SEI.
Ah, the SEI layer. We hear about that a lot.
Exactly. This very thin layer acts like a protective skin, preventing further unwanted reactions between the electrode and the electrolyte while still allowing lithium ions to pass through.
Okay.
Also, some salts help form a protective layer on the aluminum current collector, preventing it from corroding. So, a bit of breakdown, but in the right way.
Okay, let's talk about specific salts then. The chapter starts with lithium perchlorate, LiClO₄. You mentioned it was studied a lot in the past. What made it interesting back then?
Yeah, back in the 70s and 80s, LiClO₄ was appealing. mainly because it offered high ionic conductivity, meaning ions could move through the electrolyte easily.
Got it. Faster movement.
Right. It also dissolved well in the solvents they were using at the time and showed pretty good thermal and electrochemical stability. Plus, it helped form a decent SEI layer.
So what went wrong? Why isn't it in our phone batteries today? Sounds like it had potential.
Two main issues, really. First, LiClO₄ didn't do a great job of protecting the aluminum current collector. It led to corrosion over time.
Not good.
And second, and probably more significantly, the chlorine in LiClO₄ is in a very high oxidation state. That makes the whole molecule a strong oxidizing agent.
Oh.
Yeah, this raised serious safety concerns because it could become explosive under certain conditions. Just too risky for widespread commercial use.
Okay, that makes sense. Too dangerous. Then we have the current king of the hill, lithium hexafluorophosphate, LiPF₆. What's its secret? Why is this the one?
Well, LiPF₆ has proven to be the best all-around performer so far. In the non-aqueous solvents used in lithium-ion batteries, it provides electrolytes with really high conductivity.
Okay.
And importantly, it also reacts in a way that forms a stable protective layer on the aluminum current collector, preventing that corrosion issue we just talked about.
Ah, so it solves that problem.
Exactly. It's not perfect. It can be a bit sensitive to moisture, for example, but it strikes a really good balance of all the necessary properties.
The book shows figure 1.3 with the structures of some of these common anions as F6-Air, PF6-Air, ClO4, BF4A, and SO3CF3A. Seeing the actual shapes, it kind of gives you a better sense of how they might interact with lithium ions and solvent molecules.
Absolutely. Visualizing the structure helps. And while the captions might mention other salts, the key takeaway here is understanding the chemical structures that give rise to the properties we want, and why LiPF₆ really emerged as the dominant player after the drawbacks of earlier ones like LiPF₆ became clear.
Okay. The chapter then moves into more experimental territory, looking at advanced salts like fluoroborates and fluorophosphates. Are these the potential successors to LiPF₆, like the next generation?
They could be either as direct replacements or, maybe more likely initially, as additives to enhance LiPF₆'s performance. One example discussed in detail is tetrafluoroborate, BF4A.
Okay.
What's fascinating is that the way the lithium ion interacts with the BF4 anion in solution isn't always the same. It can vary quite a bit. Figure 1.6 illustrates these different modes of interaction.
Different ways they hang out together.
Pretty much. From the lithium ion being completely separated by solvent molecules, that's called solvent-separated ion pairs, or SSIP, to various degrees of direct contact ion pairs, or CIP, and even larger clusters of ions, which they call aggregates, or AGG.
And these different arrangements actually affect how we can study them, like with Raman spectroscopy. You can see the difference.
Exactly. Figure 1.6 also shows how the signals we get from Raman spectroscopy, which basically tells us about the vibrations of molecules, shift depending on these different coordination environments. It helps researchers understand what's happening at the molecular level in the electrolyte. It's quite powerful.
So it's not just about the salt itself, but also how it behaves in the specific solvent it's dissolved in. The whole mixture matters.
Precisely. Figures 1.8 and 1.10 demonstrate how the arrangement of solvent molecules around the lithium ions and the overall structure of the solution can influence how easily ions can move, which directly impacts conductivity. Figure 1.11 then compares the conductivity of different lithium salts in acetonitrile at a specific temperature, highlighting that while LiPF₆ performs well. Figure 1.9 reminds us that it also leads to higher viscosity.
Ah, so it makes the liquid thicker, which could slow things down.
Exactly. It can hinder ion movement. It's a constant balancing act. Figure 1.17 then shows how scientists are trying to fine-tune the properties of anions like BF4-Air and PF6-Air by attaching different fluorine-containing groups, trying to get the best of both worlds.
Tweaking the structure.
Yep. And figure 1.08 shows even more variations on this theme. Lots of clever chemistry going on.
Next, the chapter dives into some pretty complex-sounding chemicals, perfluoroalkylacetates, sulfonates, and tephosphates. What's the key idea behind these? They sound like a mouthful.
They are. The perfluoroalkyl part basically means they have chains of carbon atoms, where all the hydrogen atoms have been replaced by fluorine atoms.
Ah, lots of fluorine.
Right. And fluorine can have a dramatic effect on a molecule's properties. Figure 1.1 shows that these types of compounds tend to have very high gas phase acidity, which, as we discussed earlier, can be an indicator of how their anions might behave in terms of releasing lithium ions.
Okay, linking back to that acidity idea.
Exactly. However, the fluorocarbonate anion, CO2-ADF, is noted for being quite reactive, so that's something to watch out for.
And we also see phosphoryl imide anions in figure 1.24, which look even more intricate, just more complex structures.
These are examples of how researchers are exploring more complex molecular architectures for anions. They're hoping to achieve specific properties, maybe better stability, maybe better conductivity that might lead to improved battery performance or safety. Figure 1.25 gives a detailed structure of one such anion, just to give you an idea.
Okay. The chapter then talks about organoborates, alloganophosphates, and aluminates. This sounds like it's bringing organic chemistry principles, like carbon structures, into the design of battery salts.
Exactly. This involves incorporating carbon-containing groups into the structure of the anion. The chapter highlights some early work from the mid-90s, using boron-chelate complexes, where the boron atom is bound to other atoms in a ring-like structure, kind of like a claw holding the boron.
Okay.
Lithium bis 1-son-2 benzenidylato-2, or LiBOB,
LiBOB, gotcha.
shown in figure 1.26a, was an early example. It had good solubility, but its oxidative stability wasn't great. Figures 1.26 and 1.28 showcase a whole variety of these chelated organoborate anions, including one called BUBIR and its fluorinated derivative DFOB.
BUBIR, okay.
Yep. And figure 1.32 shows organophosphate anions. Figure 1.33 briefly touches on organoaluminate anions. The key here is the ability to potentially tailor the electronic and structural properties of the anion through these organic modifications. More levers to pull, basically.
Finally, Chapter 1 touches on some other, maybe more exotic anions, including methide anions with nitro and cyano groups, some of which are apparently so energetic they might be useful in rocket fuel.
That's right. Sometimes the hunt for extreme properties for other applications, like propellants, can lead to interesting discoveries for battery science, even if those specific compounds don't end up being used in batteries themselves.
Sure.
The chapter mentions that some cyano-containing anions haven't seen widespread use in batteries due to their electrochemical stability compared to other options. They might break down too easily at the voltages batteries operate at.
Okay.
The chapter then concludes by briefly showcasing even more reported anions in figures 1.4 and 1.41, where, the understanding of their properties is still developing. And it circles back to the idea of how the acidity of the precursor acid influences how much the ions in the salt tend to associate with each other in solution. That ion pairing thing again.
Okay, wow. That was a really deep dive into just the lithium salts. Feels like we covered a lot of ground.
It's a complex area.
Now let's move on to Chapter 2. Non-aqueous electrolytes with advances in solvents. This chapter has contributions from several experts: Dr. Makoto Ue, Emeritus Professor Yukio Sasaki, Professor Yasutaka Tanaka, and Professor Masayuki Morita.
Right. A team effort on this one.
So if the lithium salt provides the charge carriers, the solvent is the medium they travel through, right? The liquid part.
Precisely. This chapter focuses on the liquid environment in which the lithium salt dissolves. It reviews recent progress in using organic solvents that contain elements like sulfur, fluorine, boron, and phosphorus in lithium cells.
Other elements besides just carbon, hydrogen, and oxygen?
Exactly. Introducing these different atoms into the solvent molecule can significantly alter its properties, like how well it dissolves salts, how conductive it is, how flammable it is, and how it interacts with the surfaces inside the battery. As the chapter points out, almost all commercial lithium-ion batteries rely on these non-aqueous electrolyte solutions. Even the gel-like electrolytes used in some polymer batteries are essentially organic electrolytes trapped in a polymer matrix, still based on these liquids.
Let's start with fluorine-containing organic solvents. We saw fluorine playing a big role in the salts.
Yeah.
What advantages does it offer in the solvent itself?
Well, fluorine can bring several benefits to solvents, too. It often makes them less flammable, which is a huge plus for safety. It can also improve their stability in high voltages and can influence the formation of that crucial SEI layer we discussed earlier, sometimes in a good way.
Okay.
The chapter reviews various types of fluorinated solvents, cyclic esters called lactones, linear and cyclic carbonates, and ethers. Scheme 2.1 actually shows some ways these fluorinated lactones can be made if you're into the chemistry details.
The chapter even includes diagrams and data like figure 2.2 showing the phase behavior, basically how liquids mix or separate of a common mix of three solvents, EC, DMC, and EMC. And table 2.2 details how well LiBF₆ conducts in mixtures of EC and EMC.
Absolutely. It really highlights how the choice of solvent mixture can impact performance. It's rarely just one solvent.
Right, it's a cocktail.
Exactly. The chapter highlights specific fluorinated ethers like MFE and EFE. They mention their non-flammability and low viscosity, which is good for ion movement,
Okay.
but also their limited ability to dissolve lithium salts on their own. So you often need to mix them with other solvents, like linear carbonates, to create safer solutions with reasonable conductivity.
A trade-off again.
Always. The fact that LiPF₆ batteries using a specific fluorinated ether mixture showed good cycling performance and safety is a promising sign for these types of solvents. Figure 2.0 provides a nice visual of the structures of many common and experimental solvents, both fluorinated and not.
Next up are sulfur-containing organic solvents. This seems like a less obvious choice than the carbonates that are so commonly used in today's batteries.
Well, while carbonates are indeed the workhorses, sulfur-containing solvents, particularly a class called sulfones, have shown real potential, especially for batteries that operate at higher voltages.
Higher voltage? Like for more power or energy?
Generally, yes. Higher voltage can lead to higher energy density. The chapter reviews different types of organosulfur compounds, and Table 2.8 gives a rundown of their physical properties, melting points, boiling points, that sort of thing.
Sulfones like ethylmethylsulfone and sulfolane are mentioned. What makes them interesting for these high-voltage applications?
Primarily, sulfones generally exhibit good stability at high electrochemical potentials. That means they can withstand the higher voltages required by some advanced battery chemistries without breaking down.
Okay, they don't decompose easily.
Right. Table 2.1 lists properties of various sulfone derivatives, and figures 2.36 and 2.37 show how well a particular lithium salt conducts in different sulfones. Interestingly, though, while sulfones tend to be stable at the positive electrode, their ability to form a good protective SEI layer on the negative graphite electrode, well, it varies significantly depending on their specific chemical structure.
Ah, so they might be good on one side but not the other.
Potentially. For example, ethylmethylsulfone, EMSO2, doesn't seem to form a very effective SEI on graphite, which is a problem.
So they might not work as the sole solvent in a battery then. You couldn't just use pure sulfone.
That's often the case, yes. The chapter discusses how mixing sulfones with low-viscosity solvents can improve the overall performance, better conductivity, better wetting of the electrodes.
Okay.
The example of using LiBF₆ in a mister containing a sulfone and another solvent for a high-voltage battery demonstrates this approach. There's also a bit of debate discussed about the stability of different types of sulfones, highlighting the complexity of predicting solvent behavior just from the structure.
Right.
The section concludes that while sulfones alone might have limitations, using them in combination with other solvents and additives can unlock their potential. And there's ongoing research into new sulfone derivatives, maybe with fluorine or other groups attached, aiming for even better properties.
Okay. Finally, in Chapter 2, we look at phosphorus-containing organic solvents. Phosphorus compounds are often used as flame retardants in plastics and things. Is that their main role in batteries too? Safety.
That's a key reason why they're of interest, yes. These solvents are primarily explored as flame retardant additives or co-solvents to improve battery safety, make them less likely to catch fire.
Makes sense.
The chapter focuses on alkyl phosphates, with trimethyl phosphate, TMP, as a prominent example of a non-flammable liquid that could be mixed into electrolytes. Figure 2.22 actually illustrates the proposed mechanism how these phosphorus-containing molecules can help to quench flames by trapping highly reactive chemical species like H radicals that propagate combustion.
So adding these could make our devices less likely to catch fire if something goes wrong.
Potentially, yes. That's the goal. The chapter also discusses gel electrolytes that incorporate TMP. These are created by trapping a liquid electrolyte containing TMP within a polymer network, making it sort of like a jelly.
Okay, a gel instead of a pure liquid.
Right. It turns out that you need a significant amount of TMP. The chapter mentions at least 20% by volume to achieve non-flammability. Figure 2.28 shows that while adding TMP can slightly decrease the ionic conductivity.
It slows the ions down a bit.
A little, yeah. But it still remains at reasonably high levels. And figure 2.29 provides an interesting result, showing that even in these TMP-containing gel electrolytes, adding vinylene carbonate, VC, remember the name?
Yeah, the SEI former from earlier.
Exactly. Adding VC as an SEI modifier helps maintain good performance of graphite electrodes over many charge-discharge cycles, even comparing favorably to traditional liquid electrolytes. So you get safety and decent performance.
That leads us nicely into Chapter 3, Additives for Li-ion Electrolytes since 1990. This chapter is by Dr. Koji Abe from UB Industries. Additives. These sound like the secret ingredients, the special sauce that really fine-tunes a battery's performance.
In many ways, they are. You usually only add small amounts, maybe a few percent, but they can have a huge impact. Dr. Abe's chapter reviews the significant progress in electrolyte additives since 1990.
Okay.
He focuses on additives that have seen real-world application long seller items, as he puts it, or were designed to overcome the limitations of earlier attempts. He organizes them chronologically and draws heavily from patent literature, which makes sense coming from industry.
Right, practical application focus.
Yeah, he explains that the detailed chemical mechanisms are often found in the reference research papers. His focus is more on what works and when it was discovered.
The full section focuses on additives for the anode, the negative electrode, and vinylene carbonate, VC, is highlighted again as a crucial discovery. Why is this single molecule so important? We just heard about it with the gels.
Yeah, VC is a big one. Discovered by Sanyo Electric back in 1992, it has become a foundational additive in lithium-ion batteries. It was further found by Saft in 1994 that adding just small amounts of VC to carbonate-based solvents helps to form a stable, protective SEI layer on high crystallinity graphite anodes.
Okay.
This layer forms at relatively high voltages and prevents the continuous decomposition of the electrolyte, which would otherwise just consume the electrolyte and lead to rapid battery degradation. Mitsubishi Chemical also published significant work on this in 2004.
So it's a key ingredient for building that essential protective layer on the negative side of the battery, especially for graphite.
Exactly, a cornerstone additive. The chapter then discusses cyclic carboxylic acid anhydrides, like succinic anhydride and maleic anhydride, discovered by Mitsubishi Chemical in 1999.
Or complex names.
Yeah. These were found to be effective at preventing the breakdown of a specific solvent, procaryl carbonate, PC, when used with graphite anodes. PC is a good solvent in some ways, but it can cause graphite to exfoliate, basically fall apart, so these anhydrades help to prevent that specific problem.
Got it. Solving specific solvent-electrode interactions. Next, the chapter talks about oxalates, discovered by UB Industries and Mitsubishi Chemical in the early 2000s.
Yes, compounds like dipropergel oxalate, methylpropergel oxalate, dialkyl oxalate, and asymmetrical oxalates like methyl oxalate, often used together with VC.
Combinations.
Right. They were found to improve battery performance and stability, likely by further modifying that SEI layer or improving the properties. The chapter also briefly touches on other types of anode additives, including those with unsaturated carbon bonds and those containing sulfur, halogens, phosphorus, or nitrogen, providing examples of their chemical structures like compounds 91 through 97, just showing the variety being explored.
Chapter 3 then shifts to additives for the cathode, the positive side. Are the challenges on the positive side of the battery different? Do you need different additives?
Yes, generally. While both electrodes react with the electrolyte, the degradation mechanisms of the cathode tend to be different, often involving oxidation or reactions with the transition metals in the cathode material.
Okay.
The chapter briefly mentions sulfur-containing compounds that can act like poisons, deactivating reactive sites on the cathode material that might cause problems, and also aromatic compounds that can form conductive films, perhaps protecting the surface. Though, as you said, specific structural details aren't provided in our excerpt here.
The final section of Chapter 3 covers additives for safety improvement, which is obviously a huge area of research, maybe more important than ever.
Absolutely. As batteries become more powerful and store more energy, safety becomes even more critical. This section discusses additives designed specifically to prevent overcharging, others that contribute to non-flammability, which we touched on with phosphorus compounds, and some other miscellaneous safety enhancers.
Overcharging sounds particularly bad. What happens there?
It can be very dangerous. It can lead to excess lithium being pulled out of the cathode, potentially causing structural collapse and oxygen release.
Oxygen release inside a sealed battery.
Yeah, not good. It can also lead to lithium metal plating on the anode, which can grow dendrites and cause internal short circuits. All of this can lead to thermal instability and exothermic reactions, basically, the battery heating up uncontrollably, potentially causing fires or explosions.
Okay, definitely want to avoid that. What kinds of additives help prevent overcharging?
The chapter mentions fluorinated cyclohexylbenzenes, discovered in 2002. These can act as redox shuttles molecules that get oxidized at a specific voltage just above the normal charging voltage.
How does that help?
When they get oxidized at the cathode, they travel to the anode, get reduced back, and travel back again. This creates a sort of internal short circuit that dissipates the excess charging energy as heat, preventing the battery voltage from rising much further.
Clever, like a safety valve.
Kind of, yeah. It also discusses other compounds like 2,5-tetrate-butyl, 1-4-dimethoxybenzene, which could be useful for lithium iron phosphate, LiFePO of cathodes, and phenothiazine compounds, which were shown to be effective by Jeff Dawn and his team in the mid-2000s. Different molecules, often working by similar principles of getting oxidized at a set voltage.
Our final chapter for this deep dive is Chapter 4, Recent Advances in Ionic Liquids for Lithium Secondary Batteries, by Dr. Hajime Matsumoto from ACE in Japan. Ionic liquids. These sound like a completely different approach to battery electrolytes compared to the salts dissolved in organic solvents we've been talking about.
They are indeed. Ionic liquids, or ILs, are essentially salts that are liquid at or near room temperature, or at least below 100 degrees C. Think of molten salt, but stable at much lower temperature.
Okay, aqua salt.
What makes them so interesting for batteries is a unique combination of properties, including extremely low vapor pressure, which makes them virtually non-flammable.
Safety again.
Big safety advantage. They also tend to have wide electrochemical windows, meaning they're stable over a broad range of voltages, both high and low. And they have the potential for high ionic conductivity because they are literally made of ions.
So they could potentially address both performance and safety concerns, maybe even better than additives?
That's the hope, or at least part of the motivation for researching them. The non-flammability is a particularly attractive feature. The chapter discusses different types of ILs, especially those with imide anions like TF2Na, often combined with various aliphatic onium cations. Those are organic ions containing elements like nitrogen or phosphorus, but in a different structure than the phosphorus solvents we saw earlier.
Okay.
One challenge mentioned is the difficulty in purifying some ILs. Impurities, even small amounts, can really negatively affect battery performance. Purity is critical.
We also see a comparison between ILs with different anions like BF4 and TF2N. Does the anion matter as much here as it did with the regular salts?
Oh, absolutely. Just like with lithium salts, the anion structure massively influences the properties. For instance, ILs with BF4-based cations tend to be much more viscous, much thicker than those with TF2Na-based cations.
And viscosity affects conductivity.
Right. Higher viscosity generally means lower conductivity because it's harder for ions to move. Interestingly, ILs based on specifications called aliphatic quaternary ammonium, or AQA, chelations show wider electrochemical stability windows compared to some other common ILs.
Okay.
Furthermore, it's been observed that lithium metal can be deposited and stripped, plated, and removed more cleanly in some AQA ILs without needing additional organic additives. That's potentially a significant advantage for developing lithium metal batteries, which promise higher energy density.
Interesting. Enabling other battery types.
Potentially. The chapter also notes that adding lithium salts to these ILs, using the IL as the solvent for a lithium salt, can further enhance their electrochemical stability, particularly at the negative electrode. So you might have an IL and a lithium salt. Finally, the chapter briefly mentions other types of ILs based on different fluorinated anions, just highlighting the ongoing exploration in this area. It's a very active field.
Wow. We've really journeyed through a vast landscape of electrolyte materials today. It's incredible how much goes into that liquid inside the battery.
It really is.
From the foundational lithium salts providing the ions, to the crucial solvents they swim in, the strategically employed additives that fine-tune everything, and now these exciting possibilities with ionic liquids.
Indeed. It's clear that the electrolyte is far from a simple component. It's a complex and dynamic system. The interplay between salts, solvents, and additives dictates the overall performance, the safety, the cost, and the longevity of lithium-ion batteries. The research we've discussed in these first 4 chapters of Electrolytes for Lithium Batteries really lays the essential groundwork for understanding the ongoing advancements in this critical field.
And it's a field that's constantly evolving, isn't it? Driven by the ever-increasing demand for better batteries, longer lasting, faster charging, safer to power our devices, our cars, maybe even the grid eventually.
Absolutely. Scientists around the world are continuously searching for new materials and innovative combinations to push the boundaries of what's possible with electrochemical energy storage.
So as we look ahead, maybe a final thought for you listening, what kind of breakthroughs in electrolyte materials do you think could fundamentally reshape battery technology? Will we see a radical shift towards something entirely new, like maybe solid-state electrolytes, which we haven't even touched on here?
A big question.
Or will it be more gradual improvements through the continued optimization of these existing liquid systems? Better salts, better solvents, smarter additives. And how will those critical trade-offs between performance, safety, and cost influence the direction of this research. It certainly gives you a lot to ponder.
It does, and it underscores just how vital and, frankly, fascinating this area of material science is for the future of energy storage.
Yeah.
So much chemistry packed into that small space.
Thank you for taking this deep dive with us. We hope this exploration into the core components of lithium-ion battery electrolytes has provided you with some valuable insights into this essential technology.